Awesome, yes. Right, so the next speaker is Pratishtha. She's going to be talking about trigger fragmentation in self-gravitating protoplanetary disks. So the floor is yours.
Thank you. Hello, everyone. I am Pratishtha. I am a PhD student, second year, and with the astronomy and astrophysics group. It's a real pleasure to be here virtually, even though I can be there in person. And today I'm going to be talking about trigger fragmentation in self-gravitating disks. And so, yeah, let's get right into it. The notes. Okay. So as we know, when a molecular cloud collapses to form a star and the surrounding material flattens into a disk, that disk forms the birthplaces of planets, which is why we're really, really curious about what goes on in those disks. And I'm not going to spend a lot of time in that introduction because most of us are familiar with it. And observations have revealed structures like rings, cavities, gaps, and spirals. And to understand the origin of the diversity of planetary systems that emerge out of such disks, we also need to understand structures that we have observed in disks. And to do that, we also have some disks that show that showed signs of a self-gravitating phase. Disk undergoes a typically young and massive protoplanetary disks undergo a self-gravitating phase where the self-gravity of the disk becomes important relative to that of the star. And some disks have shown us signs of a self-gravitating phase. For example, this is a triple protostellar system, L14481IRS3b. And we can see these spiral structures here, where and the second image is that of LIS27. And we can see these spiral structures here intersecting with a gap. And so we're interested in it because it's short-lived and it might not be always able to observe it. So we want to simulate, do our best to simulate and see what happens in that self-gravitating phase, because disks can fragment, which was shown in 3D hydrodynamic simulations by Miru and Wade in 2010. So I'm going to play this movie here, where we have a self-gravitating disk where fragments will be forming, which can lead to form giant planets. Right about now. So we can see that this forms spiral structures, and the spiral structure then form fragments. There will be opacity, the stellar radiation, and several other parameters to see what conditions for a fragment form under. And following the study in 2015, did these simulations where she showed the formation of the first fragment leads to the formation of fragments in a disk. So what we're looking at here is 3D SPHNG simulations, where we already simulate a self-gravitating disk, and we simulated such that it has the propensity to fragment. Then in the first panel here, we just have the self-gravitating disk with some features, but no fragments yet. Then when it fragments the first time, forms the first fragment. And because of the formation of this first fragment, Farzana found out that it pushes a lot of material inside, which then condenses into the second spiral arm that we can see in this third panel, which eventually forms a second fragment and more fragments. So the idea was that if a first fragment forms in a disk, then it triggers the formation of subsequent fragments in the disk. And this very interesting result was supported by the stability parameter Q, which is given by the sound speed, the epicyclic frequency, and the surface mass density. And fragmentation in a disk happens when this value of the tuning parameter Q falls below 1. So we can see that there are two important parameters need to increase or decrease for Q to go below 1. First is the sound speed. If the sound speed decreases, then Q will go below 1. Or if the surface mass density increases sufficiently, the Q will go below 1. When in the previous results that we saw, Farzana explored the movement of matter in the disk, which is essentially exploring the surface mass density effect that leads to triggered fragmentation. my job for the past year has been to reanalyze these results and figure out whether or not it is just the surface mass density that motivates triggered fragmentation, or is it the sound speed as well? So for that, we do a reanalysis of the simulations that Farzana did, and we plot the two parameter, the sound speed and the surface mass density. I'm not sure why the slide order is not working properly, but bear with me, please. So we have two simulations in here. The first simulation that we see over here is that of a 1.5 solar mass star with a 1.1 solar mass disk. And we can see that in this simulation, the two fragments at about 50 AU and at about AU. And we can see that the Q falls at several locations in the disk. When we go from the purple to the red, we're essentially going forward in time. And yeah, we can see that the Q is going on at several locations in the disk. Specifically at about 24 AU, the Q decreases by 10%, which then eventually forms the second fragment. So we are looking at the sound speed. At about 24 AU, the sound speed decreases roughly by, I'm unable to read the correct percentage yet. The sound speed decreases by 5% over here, and the surface mass then also increases by 5%. I'm not sure why the text is not working properly. Really sorry about that. But yeah, essentially the sound speed and the surface mass density at the location of the second fragment, sound speed decreases by 5% and surface mass density increases by 5%, conveying the message that both the sound speed and the surface mass density contribute almost equally to the decrease in the tuned parameter, which means both of them have the potential to contribute to triggered fragmentation. Whereas in, I will get back to this graph, whereas in simulation 2, where we have one solar mass star with a 0.9 solar mass disk, we see that the Q has a much more like dramatic drop at the location of the second fragment, which in this case is at 10 AU, and decreases by 40% at the location of the second fragment, where the sound speed only decreases by 2%. These are all, by the way, and the surface mass density increases by 54%. So in this case, only the surface mass density, which is the movement of material, is significantly contributing to this decrease in Q. So what we see in these two simulations, both of them have the potential to contribute, which has not been seen before. And some other times, there's a chance that one of them may dominate. And to explore why that might be happening, we were looking at where all these particles that go inside the fragment are coming from. So to see why CS decreases in the first simulation, we have these two graphs where delta is reading. Delta temperature between of the particles after the first fragment forms and before the second fragment forms. So any negative temperature shows that the particles have cooled down between the formation of fragments. And this is for simulation 1, and we can see all near the star, as we would expect that and cooling because we're close into the star. But for a little bit further out, especially at the location of the second fragment here at 24 AU, we see this great drop, mostly decrease in T or temperature, which means the general trend of the disk at the location of the fragment is also cooling. But specifically looking at particles that go inside the fragment to make up the second fragment, we have this right plot, which again shows delta T versus R, but specifically for the particles that go inside the second fragment. And we can see that these particles are coming from outer radii quite a lot. So beyond 24 AU, we have all of these particles all the way up to 80 AU that come in from the outside of the disk to the inside of the disk to form the second fragment, which means that cooler is moving into the disk, which is cooling down the disk. That is one of the reasons. The other thing that we saw is all of these particles that go to the fragment, about 50% of those particles are going up and down in the disk. And in the self-gravitating flared disk, the upper layers are typically cooler. So when these particles go from the midplane to the top of the disk or the bottom of the disk and interact with the so-called boundary, then they cool down. So about 50% of these particles are also cooling down due to interactions with the boundary. And the rest 50% of them are just cooling down because cooler material from the outside is moving in. So with simulation one, we have a very nice story about is decreasing, both of them contributing, and why that's happening. But for simulation two, when we look at the same kind of curves, we have again delta t versus r with different locations of the formation of fragments. And if we look at this location about at 10 AU, where the second fragment forms simulation two, we can see that global nature of the disk is both heating and cooling. So there is not just cooling or maintaining of the temperature that's happening in this case. There's both heating and cooling happening globally in the disk, which is the left picture. For looking at the particles that go specifically into the fragment, we have the right graph. And we can see that here most of the particles are either maintaining their temperature or cooling down, which means that the particles into the fragment are forming out of preferentially cooler material, even though the disk general nature is not cooling. So in this case, the fragment still forms, there's still triggered fragmentation, but then the cooling was not. And in this case as well, we want to know just by any of these particles would cool down at a location that is so close to the disk. So we explore the interaction with the upper layers as well. And in this case also, we find that about 50% of the particles interact with the upper and lower boundaries of the disk and cool down. So yeah, our main concluding remarks are that both the CS and the sigma can contribute to triggered fragmentation, which has not been demonstrated before. We also find that fragmentation is stochastic. That in some places we have a very clear picture of what's happening, a global cooling trend, and that global cooling trend contributing to cooling and everything. But in the other case, even when there is no global cooling happening at the location of the second fragment, we still see that fragmentation can happen, and a second fragment can form out of preferentially cooler material. And then we find that boundary interaction might contribute to cooling, but there's a caveat there that matters a lot. That is the way that model where the outer layer of the disk lies matters a lot in this case, and our prescription is simplistic. So if anybody wants to explore this precise or more sophisticated boundary particle interactions, it will be very helpful in concluding whether or not that happens in all cases. Plus, I would also like to express that we've done this for 2 simulations, which was good enough to demonstrate that both CS and sigma can contribute, but a whole suite of simulations can be performed, such as with different disk masses, with different disk to star mass ratios, with different opacities, maybe, to figure out in which cases exactly is sigma the dominant factor or both of them can contribute. So yeah, that's about my work, and we have a draft in the making for the paper, and more to every. We also have some work in phantom ongoing right now. I'm very new to phantom. Please don't ask me a lot of phantom questions. But yeah, my current work is about gravitational instability disks with warps. And you all know Sal. Sal has done some excellent work with warps in self-gravitating disks. What I'm going to do is to add some dust into his work. So these are panels from Sal's paper from the left to the right, where in the left panel, we have a warp in a self-gravitating disk. And then that warp, when it goes away, it takes, there are no spiral structures left in the disk. But then if you give the disk more time to evolve, the spiral structures come back. And these were the key results that Sal showed with his work. I currently figure out whether or not the same thing will happen if the disk has both gas and dust. So yeah, only Phantom will tell what happened there. And that's it about my work. Thank you so much for listening, and please let me know if you have any questions.
Thank you very much, Pratishtha. We are well ahead of time still, so we've got plenty of time for questions. Does anyone have any questions for Pratishtha? Go ahead.
Hello, nice talk. Which prescription of cooling are you using for your simulations here?
We're using radiator transfer.
Okay. Thank you.
I've got also a question. So I'm not quite sure I get the difference in the setup between the two cases, the triggered and the non-triggered. So the disk mass is the same in both cases, but then when you inject a single particle in the second case with the trigger? Or how, like, what's the difference in the setup between them?
Oh, the disk mass in the two cases, simulations have different star and disk. The first one is a 1.5 solar mass star with a 1.1 solar mass disk. The other one is a 1.1, sorry, not 1.1, 1 solar mass star with a 0.9 solar mass disks. So the disk to mass ratios are roughly 0.7 and 0.9.
Right, so the different disk masses.
Yes.
And so one fragment's easier and that triggers further fragmentation. That's the idea.
Well, different things are happening in both disks, and it's which is why I said a suite of simulations which explore more a bigger parameter space would be very useful, because what we're seeing is happening in just cases, and in just two simulations. So it's hard to point out exactly in which case, or for example, which regime of the disk to star mass ratio would this be, would one factor dominate and the other not. So yeah, a broader set of simulations would be very useful to that.
Right, we've got a question. Thank you very much, Pratishtha. We've got a question from Guillaume.
Hello. I saw previously that the opening of the inner cavity in the disk was a numerical effect.
Sorry?
In the disk, in the inner disk, you have the opening of a cavity. And previously, I thought that it was a numerical effect due a low treatment, cheap treatment of the radiation, of the thermal effects. But here, you said that you are using radiative transfer. So do you think that this cavity is physical?
Could you repeat that, please? Could you tell me which graph so I could put it up on my slides as well?
Yes. So there is an inner cavity in the disk. So can you hear this?
Yes.
There is an inner. Yes. So there is an inner cavity in the disk at the inner radius. Okay. And before I was thinking that it was a numerical effect, and that it was due to a low treatment, a poor treatment of the radiative transfer. But now you are saying that those simulations are done with radiative transfer. So do you think it's physical?
Oh, where in the disk did you observe a cap?
In all disks?
Sorry?
In all disks.
In all disks. Yeah, well, you run the simulation, you see that there is an opening of a cavity in the center.
If you could show slide 6 again.
Face on view of the disk.
This one?
Yeah.
Yeah.
Well, in the last slide, for example, there is a big cavity, no? In the last one. No, yeah, the last slide, sorry, there were 3 disks.
The warps.
Oh, okay. Maybe I missed this then. Okay, so sorry, I missed the point. Sorry.
Got time for more questions if anyone has any pressing questions.